So in the outline on slide 15, we now turn to the antisocial behavior example in the reduced version, the smaller sized version. And we're going to focus on latent class probabilities and particularly on C on X results, regressing the latent classes on the covariates. On slide 16, you have the data set, ASB free, and the use variables that we're going to work with are these 7 latent class indicators and these 7 covariates. So this reduced set of 7 U's and 7 X's is perhaps more typical numbers of indicators and covariates that you will have in your data. It's not often maybe that you have 17 U's and 11 X's. So maybe this is a more typical example. The categorical variables are still the latent class indicators, and here are 2 setups on slide 17 where we regress all latent class indicators on all covariates. First, in a regular run, all U's and all X's, where we have a mixture and a good number of starts, and we have C on X, and then also U on X. Now the PSEM run corresponding to that same model is adding to the direct effects regressions here, labels and model priors. So this is all you have to do here. D1, direct effect 1 to 49, there are 7 U's, 7 X's, 7 times 7, 49, and we choose a prior of 1.0 in this case. And that's all you have to do to turn the non-PSEM run on the left into a PSEM run on the right. The computing time here is 1 minute, and you can note then that the larger set, 17U, 11X's, took 11 minutes. So the number of variables makes a difference, and I would say these runs are a little bit slower than what typically would be expected because the sample size is large, over 7,000 people. So slide 18 then, we have this log likelihood graph again, the log likelihood on the y-axis and the prior variance on the x-axis. And then we have a log likelihood curve here, which we draw approximately from our results. It's not generated by Mplus. And we see that when we have an all direct effects run, the non-PSEM run with all direct effects, we get 22 significant direct effects of the possible 49. And down here we of course have no direct effects, which is a non-PSEM run, but it's the same that you would get in a PSEM run if you had a very small variance. Now this number 19 here in the middle, the fact that the number of significant direct effects does not increase monotonically here is not what we would generally expect, but it can happen. So slide 19 then gives this log likelihood table again that we saw for the full set. We have the no direct effect model with the lowest log likelihood and no significant direct effects because there are no direct effects. And then the all direct effects run with 22 significant ones. And then we do a run with only those 22 significant direct effects. And that then is the beginning of our analysis before we turn to the PSEM runs here with different variances for the priors. Here we go from 0.1 to 1.5. And we see then that the PSEM 1.0 run has 15 significant direct effects, and we get the same 15 direct effects in the PSEM 1.5 run, and here actually the 15 direct effects are the same in models 6 and 7. Turning to the non-PSEM runs down here, building on model 4 with 10 direct effects, or model 5 with 19, and model 6 with 15. We see the log likelihood, and we see the BIC values here, where the BIC seems to be the lowest for of them all for the 19 direct effects, but the 15 direct effects model comes very close. And in both cases, 19 and 15 direct effects, actually 14 of them only are significant here, you have a very small log likelihood drop as defined by this percentage here. Now let's take a closer look at these models. Why did I bold 15 for PSEM 1.0 in the graph on slide 18? So let me just go back to slide 18 for a second. Why did I bold this one and not 19 or that 15? Well, model 6 and model 7 have the same number of significant direct effects, so it doesn't matter that model 7 has a higher log likelihood, because both models lead to the same non-PSEM model 10, same direct effects. I chose model 10 because it has a small 0.2% drop in the log likelihood, it's relatively parsimonious, and is close to the best BIC. But model 9 is a strong contender, so that's the model 9 here with 19 direct effects and a 0.1% drop. Strong contender with a smaller drop in log likelihood, the best BIC, but 19 instead of 15 direct effects to consider, so not as parsimonious. Model 3 is also contender. Let's see, model 3 with 22 significant direct effects. That has a BIC that's very close to the one with 19 direct effects. So almost the same BIC as model 9, but 22 instead of the 15 direct effects. So you ask yourself, how parsimonious can you go here? How few direct effects can you get away with? And the question then is, are the extra direct effects of model 3 and model 9 relative to model 10, are they important? So I took a look at that for model 9. The fight indicator on the dropout covariate is the only noteworthy direct effect beyond those of model 10, with a fairly small probability difference for non-Hispanic males at average age 94, varying the dropout from 0 to 1. Now slide 21 gives some technical notes here. First, we talked about a number of parameters for PSEM earlier, and I wrote not available, which means that you don't get BIC either, because that is based on the number of parameters. And that's because when you do a RegSem, that is PSEM applied to models that are identified, but that you want to simplify, that doesn't have a good way of counting the parameters. Parameters, like it says here, can have tiny prior variances, with parameters estimated close to 0 and contributing nothing to fit. And we argue that these are not real parameters that should be counted, but the precise removal of these parameters is subjective, etc. You need the definition how close to 0 we really are. So it's not clear what the number of parameters is in this RegSem version of PSEM. That's one point. Another technical point is that you can come up with alternative log likelihood drop definitions. And here's one that is favored by Tiermer, where the denominator here is the difference between the model LM1, which has no direct effects, compared to the model with all direct effects. So if you go back to the slide on 18 here, we're talking about the model with no direct effects and the model with all direct effects. So as as a denominator, you look at the difference between the lowest and the highest point of the log likelihood, and then you talk about how much changes within that range for different model choices. So back to slide 21, you take your model, particular model that you're interested in, subtract it from the M2 model. Again, the M2 model is all direct effects, and then compare it to that full range of likelihood difference. That's for PSEM models, and he suggests for models, for non-PSEM models, that is models based on PSEM but not using PSEM, you have a different denominator here where you compare model 1 and model 3. So model 1 and model 3, no directs versus 22 significant directs. So that's the non-PSEM denominator. Now, in this case, then, the percent drop relative to the total possible drop should be a small value, like you can have a cutoff where you would want it to be at least no higher than 5%. So if you go back and use that new idea for the full set of variable run that we did earlier, model 11 does best, which is the same model that we chose before. So that doesn't change the choice. But here now, for the reduced set of variables, model 9 does best, the one with 19 direct effects, which has a 5% drop, whereas we chose model 10 with 15 direct effects, which has a 17% drop. So not as satisfactory in terms of a drop as model 9 with 19. But again, are the extra direct effects important? All right, now let's turn to the latent class results and the C on X results for the model I chose. So let's interpret, first of all, the 4 latent classes for this model 10 with 15 direct effects. So the classes are fighting, threatening, high on all the indicators, high on drug indicators, and low on all the indicators. So I use the output section results in probability scale, which is useful especially for binary latent class indicators. It's probability of being in the high category of the indicator, that is, you have experienced this. So class 1, the fight threat class of 0.32, 321 people. Fight and threat are high. Class 2, high on all of them. Class 3, high on pot and drug. And class 4, low on all of the indicators. So slide 24 then gives the class probabilities for this reduced model. We get the same interpretation for the different approaches here that I list. And the first approach is model 10, class probabilities with 15 direct effects, 0.321, etc. Now, if you don't include the direct effects, you get slightly different probabilities, but not a huge difference. But if you do what's often done, compute the class probabilities based on the latent class indicators only, that's certainly what we do in multi-step analysis, where the latent class indicators constitute the measurement model, which we use in the first step. Then you have a bit lower class probability for the first class and a little bit higher class probability for the last class. So there you have more of a difference in the class probabilities. Then you may want to ignore. So again, this is the model we choose. Here's the model we may pick incorrectly. Slide 25 then. The central result is the C on X, the regression of the latent classes on the covariates for this model. On the left and on the right we have the no direct effect model. And we look at class number 1, which is the fight threat class. And you see then for model 10, Hispanic has a significantly lower effect on fight threat, significant and negative. Divorce has a significant increasing effect on fight threat. But if you ignore the direct effects, you see the Hispanics have a positive effect instead of a negative, and it's insignificant. And for divorce, it's also insignificant. It has a smaller estimate, a slightly larger standard error, becomes insignificant. So this is a difference that may be important in your analysis, and this is just showing it for one class. Now, number of significant effects or covariates on all the latent classes. In the 15 direct effects model, model 10, we have 17 of them. In the no direct effect model, that is the one on the right, the total number is 13. So one can ask, why do we have fewer significant direct effects in the, fewer C on X effect, significant C on X effect for the model with no direct effects than the one with 15 direct effects? It could be that when direct effects in the no direct effects model are forced through C only, the effect of the covariate on the latent class indicators are forced to go through C only, some significance is lost. Maybe direct effects with opposite signs are present. These kinds of discrepancies up in this table at the top here were found in simulations in the 2014 paper by Tiemer and me, which is pretty much the same as WebNote 15.